Welcome to Utah State University's 2021 Design Build Fly video report. We are the Utah State University Big Blue Aviators team, and here is our submission to the American Institute of Aeronautics and Astronautics Design Build Fly competition. We will first present the detailed design of our aircraft and why we believe our design meets the competition's requirements. As you can see in these 3-view CAD drawings, Big Blue Aviators is a high aspect ratio, dual prop, cargo monoplane with tricycle landing gear, a traditional empennage configuration, and a Bond Bay style sensor deployment system. Big Blue Aviator's carbon fiber reinforced foam wing has an aspect ratio of 4 and a wingspan of 5 feet. The carbon fiber and balsa wood fuselage is roughly 6 feet long. The wood reinforced foam empennage has a 2-foot wide horizontal stabilizer and a 10-inch tall vertical stabilizer. For Mission 1, the aircraft weighs 10.5 pounds without the sensor. For Mission 2, the aircraft plus its single sensor in shipping container weighs 13.5 pounds. In the Mission 3 configuration, the plane also weighs 13.5 pounds, as the shipping container weighs less than an ounce, and we did not have any shipping container simulators for Mission 2. As you can see here, Big Blue Aviators has a traditional aircraft control architecture, including ailerons, rudder, and elevator. The blown flaps, located directly behind each motor, help the large and heavy aircraft take off within the 100-foot runway distance allowed by the competition. Our aircraft is propelled by two 1100 kV brushless motors with 10x7 propellers. These motors are powered by two 6000 mAh 4S LiPo batteries and controlled by two 80 amp electronic speed controllers. We will now discuss a few of our design decisions. The first thing we focused on was optimizing our score. Assuming our aircraft was able to successfully complete all the missions, our analysis showed there were two possible strategies for maximizing our score. A. Maximize Mission 2's score by having a sensor of minimum size but carry many container simulators, or B. Maximize Mission 3's score by having a single large sensor. We chose to design our aircraft around a single large sensor payload, as that would mean the aircraft would be carrying roughly the same payload for both Missions 2 and 3. This design allowed us to optimize our aircraft's flight characteristics for both missions simultaneously, rather than having to design the aircraft around carrying two very different payloads for Mission 2 and 3. Once we determined our aircraft needed to carry a single long, heavy sensor, we were able to begin analyzing our design trade-offs. After considering monoplane, biplane, and flying wing aircraft configurations, we chose to design a monoplane for its balance between stability, control, weight, ease of construction for rapid prototyping, and takeoff/landing consistency. For the motors, we decided to use two wing-mounted polar motors rather than a single pusher or polar motor, as it would allow us to use blown flaps for helping the heavy aircraft take off within the allotted distance. For the wing position, we chose to place the wing on top of the fuselage for its balance between the important figures of merit, as well as the clearance it would allow our wing-mounted propellers. The wing position trade study was performed in close conjunction with that of the motor configuration. Regarding the main wing's airfoil, we decided to use the NACA 6409 airfoil due to its large maximum lift coefficient and its thicker cross-section, which increases wing rigidity and construction precision. For the empennage, we chose to use a conventional tail configuration rather than a T, cruciform, or V-tail for its lack of a weight or complexity drawback. As our long, heavy sensor needed to be stable during flight, we decided to include a rear box fin. Compared to external fins on the sensor, the box fin allowed the sensor to have a constant outer diameter along its length, which cut down on shock absorption material required for the sensor container during the drop test. Having a smaller profile also allowed us to construct the fuselage with a much smaller internal cargo bay. We chose to incorporate a fixed tricycle landing gear with a steerable front gear. This type of tricycle landing gear is both simple to construct and greatly assists the pilot during takeoff and landing, both of which are vital to completing all the missions. Based on our design decision to carry a single long heavy sensor, we estimated we would score relatively lower than other teams on Mission 2 due to not having any container simulators. However, we plan to make up those points on Mission 3 due to the sensor's length and weight. As Big Blue Aviators is a relatively large cargo aircraft, we estimated it would be slower than some other competing aircraft as well. However, we expected our aircraft would be relatively consistent in completing the missions due to flying at a lower, more controllable speed. This aligned with our overall goal to consistently complete all missions, rather than optimize the aircraft to a point in which it becomes inconsistent. We will now move on to the demonstration portion of the video report. As you will see from the following tech inspection comparisons, our aircraft matches the 3-view CAD submitted in our design report. A few small tweaks were made to the wing mounting angle and horizontal stabilizer shape due to some additional recent prototyping, but the aircraft is otherwise identical to the submitted CAD design. You can see here the sensor lights being remotely activated and displaying the correct pattern during our ground mission. However, the deployment motor Arduino began malfunctioning during our flight event, so we could not demonstrate the deployment system during the ground mission, nor fly with it. We hope to resolve these issues and deploy the sensor in flight at a later date. This clip shows Big Blue aviators taking off and completing a lap in the Mission 2 configuration. As you can see, the aircraft took off before the white line, which marks the allowed 100-foot runway distance.
Yep.
Now you can see the aircraft landing smoothly in the Mission 1 configuration thanks to our fantastic pilot. During our local flight event, the aircraft successfully completed both Missions 1 and 2 with a full competition course setup. Although we are disappointed with the deployment system malfunctions, we are pleased that we were able to complete 2 of the 3 missions and still have a flyable aircraft to attempt the last mission after we troubleshoot the Arduino problems. Thank you for watching, and a special thank you to our faculty mentors, Jackson Graham, Joel Ellsworth, and Sabrina Snow, our pilot, Daniel Robinson, the USU Engineering Department, and the Bridgeland RC Club for letting us fly at their phenomenal remote control airfield. We look forward to next year's Design Build Fly competition. See you then.